So the problem we're going to look at today says HNO2 nitrous acid has a Ka of 6.92 times 10 to the negative fourth. If 100 milliliters of zero point 0.2 molar nitrous acid are mixed with 100 milliliters of zero point 0.4 molar potassium nitrite, what is the pH of the resulting solution? Assume volumes are additive. So we first need to remember that pH equals the pKa plus the log of the concentration of our conjugate base over the concentration of the weak acid. This is the Henderson-Hasselbalch equation. So pH equals. Now the pKa is the negative log of the Ka. So we take the negative log of 6.92 times 10 to the negative fourth, and we come up with 3.16. And then this is going to be plus the log. Well, if we mix these two solutions together, we will be doubling the volume, so the molarity will be cut in half. So our KNO2, our nitrite, the NO2 in particular being the key part of this, is our base. The base goes on top. So instead of it being zero point 0.4 molar, it's going to be zero point 0.2 molar. And our acid, instead of being zero point 0.2 molar, will be cut in half to 0.1 molar. And so if we put this into our calculator, it's 3.16 plus the log of zero point 0.2 over 0.1. And that gives us a pH of 3.46. Now let's ask ourselves if this makes sense. Well, if our acid and base concentrations were equal, then the numerator and denominator in our fraction would be the same. So the fraction would be equal to 1. And something you should remember is that the log of 1 equals 0. We're talking, of course, about base 10 logarithms. So in that case, the pH equals the pKa when you have equal amounts of weak acid and conjugate base. In other words, at maximum buffering capacity, whenever you have, or anytime you have equal amounts of a conjugate acid base pair, the pH of the solution equals the pKa. And in this case, since we have more base than acid, bases have higher pHs, our pH should be higher than the pKa, and 3.46 is definitively higher than 3.16.